This lecture is on the ideal characteristics of an amplifier, and what we want to do in this lecture is come up with the ideal values of input resistance, open loop gain. Okay, so A here stands for open loop gain, and we'll talk more about what's meant by open loop in future videos, but for right now just know that that's what it's called. And this is just a constant. Alright, so it's okay, so we want to find the ideal values of the input resistance, open loop gain, and also the output resistance. And to find these ideal values, we're going to analyze this circuit here. Now, what you see in blue represents some generic amplifier. So over here on the input side is just a resistance with a voltage across it defined as VI, and over here on the output side we have a dependent voltage source, that's the open loop gain times this voltage at the input across the input resistance, and then this dependent voltage source, as you can see, is in series with this resistance, that's the output resistance. So what's in blue actually represents an amplifier. Now what's in red is connected to the amplifier. So over here you can see there's some source that with a resistance that represents the signal that we want to amplify. And I purposely left this source ambiguous. Okay, I didn't define it as an AC or a DC source because these ideal values apply to no matter what type of signal we have, whether it's a DC signal or an AC signal. So this source could be either AC or DC, and it wouldn't affect anything that we do in the analysis that we're going to start here in just a moment. And then over here at the output side, this load resistor just represents whatever you're connecting the amplifier output up to. So for example, this could represent a speaker. And again, this over on the input side is a signal we want to amplify. So, as an example, this could represent a guitar pickup, for example. Okay? Alright, so let's go ahead and find these ideal values. Now, the first thing you have to consider here is, what do we mean by an ideal amplifier? Well, an ideal amplifier would make the output signal as large as it possibly could be. Okay, so ideally we want to make this signal over at the input as large as it can be over here at the output. So notice that there's two loops. Okay, there's a loop here and there's a loop here. So in this very generic type of circuit, it closely resembles the specific type of amplifier analysis we did with the BJT common emitter, because there we had two loops too, right? A base loop and a collector loop, where the base was on the input side of the circuit and the collector was on the output side of the circuit. So here in this very general case we have the same sort of thing. There's a loop over here on the input side and a loop over here on the output side. So first let's look at, well, what value of input resistance would help make V out as large as it possibly can be? Well, look, this dependent voltage source, one of the things it depends on is VI. So if VI is a big number, that's going to help V out be a large number. So what would we need in this circuit, which is just a series circuit with a source and two resistors? What would we need this resistance to be to make VI as big as possible? Well, hopefully you remember from your circuit theory that when you have a series connection like this, the largest resistance will get most of the source voltage. So we want this input resistance to be as large as possible, and ideally that would be infinity. So you see, that's one of our ideal values, is that we want this input resistance to be an open, to be infinite ohms. Because if this Ri is infinite ohms, no current would pass through RS, there would be 0 volts dropped across RS, and the entire source voltage would be across this resistor and equal to VI. And VI could never be more than VS. That's the most it could ever be. Alright, well now let's look at this constant called open loop gain. As you can see, that's the other variable that determines the value of this dependent voltage source. So we would want to have the multiplication of two large numbers, right? We already made VI as large as it can be, VS, and we would want the open loop gain to also be as large as it possibly could be, which ideally would be infinity. Alright, so both these ideal values are infinity. Now that brings us to, well, what's the ideal value of this output resistance? Well, here's V out, the signal we want to make as large as possible, and in between V out and this dependent source value, AVI, which is now as large as it possibly can be, is this series resistance R0. So ideally we would want to lose no voltage across this output resistance, because if we were to lose no voltage across this output resistance, V out would equal to AVI. So we want, in order to get 0 volts across that output resistance, it would have to be a short, or 0 ohms. Okay, and that would make V out equal to AVI. So you see, these are the ideal values of an amplifier. Infinite input resistance, infinite open loop gain, 0 ohms for output resistance. And this is going to lead into our discussion of op amps. Okay, op is short for operational, and of course amp is short for amplifier. Op amps, they don't have input resistances of infinity. However, they have input resistances that are at least 100 mega ohms. Okay, so that's million. Alright, so at the very least they have 100 million ohms for input resistance, and a lot of times it's much more than that. Open loop gain for an op amp is at least 100,000. Okay, usually it's several 100,000. And then output resistance of an op amp, it's not 0 ohms, but it's less than an ohm. You know, often a fraction of an ohm. And you see, this op amp circuit is a very practical circuit that we can build. So this very practical circuit that you can build has characteristics that, for all practical purposes, are ideal. And that's where we're going to be spending the next handful to a couple handful of videos, somewhere between maybe like 5 and 10 videos. We'll be discussing op amps and all the different uses and common applications.